deadline for completing all 12 quizzes is next Thursday at noon. And that means you should have all the quizzes done. And of course, the quizzes are explained on the class webpage. I put a link here to a Bloomberg article on methane leaks. It turns out that some of the methane leaks are actually leaks in the pipe that goes from the main pipe in the street to the individual house. And these account for a significant fraction of leaks. And methane, of course, is a very active greenhouse gas. It doesn't last as long in the atmosphere, but it absorbs more infrared light, or I should say, really, it absorbs it and then scatters it isotropically. So the greenhouse effect for one methane molecule is much greater than for one CO2 molecule for two reasons. One is that there are more frequencies that it absorbs at. But the second reason is that already we have so much CO2 in the atmosphere that the CO2 lines are already dark. And the absorption done by extra CO2 is done by, it's not absorption of the exact resonant frequency, but rather of the Doppler shifted resonant frequency due to the motion of the CO2 molecules relative to whatever the source is, typically the earth, the ground. And so, as many Bloomberg articles, they're tightly written, no extra words, no pretension, and no attempt at sending you to the dictionary for rare words, just the facts, ma'am. And another thing I'm going to show you today, well, these are 2 pages from my book, but this is the phenomenon of beats. And the graph that goes with that is here. And so there's a demo to illustrate that. Let's see, I wonder if I made this smaller. How do you make things small? I use Apple, and this is sort of a faster system.
There's a little plus and minus at the top near the words automatic zoom on the page.
The one that's
in the middle?
In the middle.
That one?
Middle.
No, like in the middle of the screen. The whole screen.
The whole screen.
This one?
Left. Keep going left. Our left.
That one?
Yeah, or to your right. Keep going to your right. It's
Oh, it's our left, your right.
All the way over here?
Oh no, on the search bar. Like, do you see where the search bar is? It's in the actual PDF file. It says automatic zoom.
Mm-hmm.
It's a PDF file.
Yeah, but no, you just passed it. You just passed it. Other way.
Other way.
The other way. Down?
No.
Okay.
Shit.
It's in the middle of the page itself, or the screen itself.
So tools? No. Oh God, there it is. Fine.
There we go.
All right, so there's a picture. There's the equation, and there's the demo. We'll get to that, I guess, a little bit later. We've got some other demos here. This, I don't know how well it'll work, but this is a demo of atmospheric pressure. We're going to, right now, the Atmospheric pressure outside is 15 pounds per square inch, and inside it's also 15 pounds per square inch, so the surface of the can is in equilibrium. It has much pressure from one side as from the other. But if I put this rubber hose on it, let's see, maybe I can put this over here so it'll be a little closer to at least some of the students. All right, now I'm going to turn on this vacuum pump and see what happens. Wow, it's pretty fast, isn't it? So the pump is in good working order. So you see, atmospheric pressure is a big deal. This is why tornadoes are dangerous. The pressure is lower in a certain region, and the force exerted is enormous on windows and so forth.
So does
What?
the atmosphere's pressure is constant.
It's at a given
Over the
altitude,
whole scale.
it's more or less constant apart from storms.
Mm-hmm. But like that phenomenon is when you have it change, like it goes lower over here and higher over here.
What, as far as I understand it, with a tornado, you've got basically a cylinder of low pressure,
Okay.
and when that goes over a house, the house just goes up it gets collapsed from the sides.
Okay. Okay, I see how it works now.
You have low pressure in the house and high pressure, normal pressure outside.
Oh, because then they're
Wham.
okay, that makes
Yeah,
sense.
and also the house can be taken up into the cylinder.
Right.
And I think that happens typically with cars. By the way, did I ever tell you the story? I must have told you the story of the Korean physicist who was 9 years old in 1945.
Not sure.
So,
All right, well, let me tell you that story. It's only obliquely related to physics. Man, I'm terrible with names, and with Korean names I'm even worse. But he's a distinguished Korean-American physicist who, well, first of all, in 1910, the Japanese took over Korea, and they turned South Korea into an agricultural region, North Korea into an industrial region, and they basically stole from both. The Japanese stole from both Koreas. And this Korean family, the father, to get work, went to Japan, settled in Hiroshima. This was the early 40s.
Okay.
And his son was this physicist, this Korean physicist I'm talking about, was 9 years old at the time. And the Korean government decided to put the children in schools outside the city. So he was in a Japanese temple that was converted into being a school. It was 9 kilometers from ground zero.
Okay.
The bomb went off, and he would have been, the kids all would have been killed if it had been an American school with glass windows. But it was a Japanese temple with paper windows. So the blast hit, blew the paper around, but the kids basically survived. The kids, I think, all survived.
Okay.
And so this man now is about 80 or 85 years of age, and he's about 80 actually. And I assume that after surviving an atomic bomb blast at the age of 9, he retained no fear of anything for the rest of his life. Okay, so The vacuum pump is working so well. Do you want to see another can demo, or shall we? Do you want to see another one? All right. Actually, I have to give candy to the person operating the camera. Ready?
I'm sick,
right.
don't worry, my reflexes are
Somebody ask
shot.
a question?
Okay.
No questions yet? All right. Okay, well, let's do the can demo
As long as it
again.
doesn't go over a ricochet
Once again,
off,
it's
and
an issue
everything's
of
good.
atmospheric pressure on the can. You want to hold the can? All right, so you can hold the can. Why don't you hold it though like that so that the camera can see you? Oh, come on, you're a good-looking guy.
Don't worry, if you want, I'll keep your face out.
That one was violent.
Well, it's pretty amazing. That's what 15 pounds per square inch does. Well, we can try to do the bell demo. This bell demo basically is that we've got a bell in here. If I turn it on, you can hear it. But now, if I can withdraw all the air, you won't be able to hear it because sound is a pressure wave in air. How well this will work, I don't know. Let's just try it. I think it is basically working. The sound is going down, isn't it?
It's attenuated a little bit, but it's still there, but it's gone down.
It's not perfect. Well, all right, let's just quit. That's basically a demo of air pressure and of sound being a longitudinal wave, a pressure wave that just goes along. In fact, we've got on the class webpage is a nice demo of such things. I don't quite remember where. Does anybody, if you see it, tell me which one it is.
For the waves?
It's
Oh, it should be. It's on the bottom of the screen. The very
bottom of the screen.
Mhm. Wave motion, right?
Movies, oh yeah, movies wave motion, I think that is right. Yeah, there we go. So this is a sound wave, and what you see happening is that the individual particles are moving back and forth, and don't really go forward with the wave. But the wave itself, the density, the plane of high density does move forward, but the individual molecules don't. So that's a sound wave. We've got other waves here. This is a transverse wave as an ocean wave. And as this diagram shows you, molecules move in circles, at least near the surface. Down below the circle, they move in ellipses or circles that are stretched in a vertical direction. And, well, I guess that's about it. So anyway, this leak, as I said to you before, tells about methane leaks, which are between the main gas line and one's house. and there are a substantial amount of the atmospheric pollution. In other words, what should be done to combat, to reduce global warming? One is switch from coal to natural gas, or even better, to solar, wind, and nuclear. The other is clean up all these methane leaks, both in cities and in the fields when the frackers are getting the methane out of the ground. So maybe we can now do the beats demo. The equation here is very simple. We can imagine that we have two sine waves. So there's a sound wave that is just sine omega 1, and I wrote x, but I probably should have written t. And if we add the two sound waves together, we have that the sound, I'll just call it B of t, is the sum of the two. But now, using trigonometric identities, one can write that as twice the cosine of omega 1 minus omega 2 times t over 2 times the sine of omega 1 plus omega 2 over 2 times t. And let's just see if I got the formula right. Yes. So this sine is just something like the average of these two. That is to say, it's the average. It's a sine wave, a sound wave of the average frequency. On the other hand, it's modulated by a cosine of their difference. And if omega 1 is close to omega 2, say omega 1 is omega 2 plus epsilon. I don't know why I'm using a Greek letter. We should try to avoid making things more complicated than necessary. So let us just say, of course the omegas are complex, are Greek also. Anyway, the sound wave is then 2 cosine of st over 2 times the sine of essentially the average frequency times time. And this is the beat then, because this is a very low frequency t, namely omega 1 minus omega 2. So we can see that, or rather we can hear that in two demos here. This is one of them. Here I can move it sort of closer to the students here. Now what we've got are two hollow boxes with open ends, and so they act as resonators. These are two resonant, what do you call them? Are they pitch? No, they're resonant...
tuning forks.
Tuning forks, thank you. And this one has an extra weight on it, so the frequency would be lower. And so I'm going to hit this one. And now I'm going to hit this one. And you see very pronounced beats where the sound almost drops to 0 and then comes back up. So let me try it again. It's not doing much. You can hear it. Yeah, it's better this time. Of course, you don't hear it. Maybe I should do it this way. Let's try it this way. right-handed.
It's going.
Well,
There it is. It's slow to go in and out.
yeah, it's maybe, I think maybe they're a little too close in they're too close in frequency because the beat thing is just so much longer. There's up on the board there is a mathematical graph I made of the beats, and it's for one omega equal to 30 and the other one 32. So that's a difference of about 1 part in 15, or maybe 7% or something. And you get one gets a huge effect. By the way, the waves that guide microscopic particles in quantum mechanics often make patterns like this. They're not longitudinal waves as the waves in three-dimensional space and time, but they can have beats like this. And if this were the wave function for some particle, the particle would be probably here or here or here or here, and very rarely there or there or there. So that's the way it works. Was that a question?
Yeah, what's the bottom axis?
X.
What does that mean?
Well, call it T if you want it to be sound.
So is it the particles are going?
Oh, if it's a particle,
I don't
if it's a particle, and if this were a wave function for a particle, then this would be, say, position X, position along a line, and the particle would be more likely to be more or less here, or here, or here, or here, and very rarely there. So the particles go where the wave function is big in quantum mechanics.
So what's the graph actually graphing?
Well, it's just the sum of these two signs, sine omega 1x plus sine omega 2x. Then there's a trigonometric formula that allows you to write that this way. Although the easy way to understand these things is to write the sine and the cosine in terms of complex exponentials. But if you just use a trig identity, you can write it this way. And then you graph that, and this is what you get. What I've got here is a demo of beats that will work better, and it works better because we can set the frequency and we can make it as loud as we want and so forth. So let me okay, now we're just hearing one frequency, and there are two speakers somewhere. I'm not sure where they are. But now, if I'm having trouble sticking this in where it's very strange here. Anyway, now we're getting the two different frequencies in two different speakers, and we get to hear the beats, and I can make the beats faster if I make the frequencies different, more different, and so I'm going to make them more different now. So you see now it's the frequency here is something times 27 for one, one of you is musically inclined and wants to play something, be my guest. Oh boy, all right.
Actually,
All right, so let me show you how we turn it on. You turn it on there and there. The signal's going from this one, it's going out there. The signal to the other speaker comes from this one, and you basically touch it there. You control this one frequency with this knob, another frequency with that knob. And then there are ranges. I'm not quite sure what the other knobs do. That's a nicer tone. Okay, we also have what we've got here is a cylinder with oil in the top, water in the bottom. Now, oil is basically CH2, water is OH2, or as we normally say, H2O. So I guess I should call the oil H2C and the water H2O. But carbon has an atomic weight of 12, oxygen 16, and that's because oxygen has 2 extra protons and 2 extra neutrons. So you go altogether from 12 to 16. So for this reason, the oil molecules, H2C, are lighter and they're above the water molecules. This also happens in the kitchen if you're mixing vinegar and oil. The vinegar is mostly water and the oil, well, is oil, so it's H2C. But now if I mix them,
I'm having too much longer.
that's great, thank you. I mix them, they, something called entropy rises. That's just essentially how many states we've got. And so this thing is all mixed up, but it's going to separate. And probably in a few minutes, we'll see the water at the bottom and the oil at the top.
Okay.
Now, there's another effect that I thought I would illustrate today. This one is somewhat mysterious. It's called the Bernoulli Effect. And the nicest way to demo it, I don't think we have such a demo, but let me show you what a nice demo is. Imagine you've got a that you've got a glass apparatus like this, and you're blowing air, say, this way, and you have fluid in this cavity here. And let's start out with the fluid like this. So if you're not blowing the air through it, the pressure would be the same in both places, and the fluid would rise to the same level. On the other hand, if you start blowing the air through this, the air, in a given amount of time, the same amount of air goes through this way with a large cross-section, whereas here, that same amount has to move much, much faster. So the air is moving much faster here, and The air here is moving like that, the air here is moving, say, twice as fast. If you do that, what happens is the fluid rises in this one because the pressure drops.
Okay.
This was an effect that was studied by Bernoulli a long time ago. One of the geniuses of the, I guess, the Renaissance. Now, I need to be able to turn this on. Yes, fortunately, there's a switch. In fact, let me move this a little closer. And this is sort of a tricky demo to do. Ball is less than on the bottom, the thing rises. Obviously, it's much more complicated than that. We've got conservation of angular momentum, set to the source of angular momentum here.
Does the Magnus effect come into play in this at all? What? Does the Magnus effect come into play in this at all? Oh, Magnus. The Magnus effect. Like if you're...
Magnets.
Oh, no, not...
There are no... Magnets?
No, Magnus. Like
okay, Magnus.
M-A-G-U-N-S. Or M-U-S.
Yeah.
M-A-G-N-U-S?
Yeah.
Yeah.
I don't know what the Magnus means. Straight in Latin.
Okay, well, apparently it's an effect. I might be saying it wrong, but if you throw somebody would go on top of a dam, for example, and throw a basketball with the rotation going towards them, and
it'll spin and go out.
Move forward,
Yeah.
rather than dropping them.
Yeah, I think that probably is true.
Okay. Well, I'm saying, like, does that have anything to do with it?
And so, yeah, I mean, it's basically, the basic effect is this. If air is moving faster here than here, the pressure here is lower than the pressure there. That's what basically happens here. All right, I think I'm going to turn this off.
That was a good one.
Yeah, this was, worked better than I thought it would. So let's see, you asked the question, so,
Thank you.
and you did a demo, right?
I'm gonna ask the question.
I'm very low on candy. I need to go to Costco again. Okay, so, does anybody have any questions, or is there something you'd like me to explain? This is not the last class, but it's the penultimate class, the next to the last class. Is there something that I forgot to explain that you'd like me to try to explain? For those who came in late, the deadline for completing all 12 quizzes is noon next Thursday. Not day after tomorrow, but the 11th of May. And there's no sit-down final exam. Everything is in these 12 online quizzes. All right. Okay, so let me then remind you of some of the basic rules that I hope you've learned here. The force on a particle of charge Q, an electric field E, moving at velocity V in a magnetic field B is that. So that's the force on the particle. And so if the field E, say, is up, and the particle is positively charged, the force is up. The particle is negatively charged, force is down, because this would be a minus sign. And if, say, the magnetic field is up, and if the particle is moving up, then there's no effect of the magnetic field, because V cross B would be zero if V and B are parallel. But if, let us say, B is up, and the particle is moving this way, and it's positively charged, then you do V cross B, and you get a force, your thumb points into the board, so it would go like that. Initially, it would turn to the right, but after it starts turning in the right, it then would be eventually moving into the blackboard. Then you would do V cross B, and now the force would be this way, so it would eventually move in a circle. If there's also an electric field that was vertical, say, then it would move in a helix, going up or down. Okay, so that's a summary of some of these electrical effects. That's what electric and magnetic fields do to particles. On the other hand, electric and magnetic fields affect each other, and in particular, charges make electric and magnetic fields. So that, for example, if you have a charge Q here, then there's an electric field. The charge is positive. The electric field goes out radially from the charge, and it falls off as the square of the distance. And the reason for that is something geometrical. It's that if you add up the electric field at the surface here times the area of the surface, that's a constant, and it's proportional to the charge inside. And in particular, the charge is positive, the electric field is moving out, and so you count that as a positive sum or integral. On the other hand, if the charge is negative, the electric field is going to be pointing in, and the electric field times the area would be negative and equal to the charge inside, or proportional to the charge inside. The actual formula is something like this. It's Q over 4 pi times the electric constant times R over the length of R cubed. So it's 1 over R squared. The electric field points in the direction of R, but multiplied by Q. So if Q is negative, E points toward the particle. If Q is positive, E points away from the particle. Moving charges make magnetic fields, and basically if you have a current, say, going this way, then it makes a magnetic field that does that. So it makes an electric field, a magnetic field that goes around the current. And we did a demo several weeks ago for 2 parallel currents. So let's try to figure out what the force would be on them. This, as I said, there's a B field that goes around it. So the B field is going into the board there. So then you have V cross B, you see the force is that way. So this is attractive. In other words, the force is that way. And the effect is mutual. This has an electric field, this current makes a magnetic field that's pointing out here. And so you have V cross B, it pulls it this way. So there's a force this way. So the two parallel wires attract each other. Anti-parallel wires would repel each other. And there are other things that happen, namely if you have a magnetic field that's going up and down, then it creates an electric field going around it. And of course the electric field will go up and down or down and up depending on a sign that I've forgotten, but I can look up. Anyway, so a magnetic field fluctuating, going from 0 to a high value, then down to 0, then down to a large negative value, and then back up again, will make an electric field that will oscillate at the same frequency, and the electric field circles around the magnetic field. The same thing is true if you have an electric field that's going up and down. This creates a magnetic field that circles the electric field and goes up and down. And in this way, high-frequency electric fields make high-frequency magnetic fields, which make high-frequency electric fields. And it's this effect that that causes electromagnetic waves to propagate. And in fact, if you put in the equations that describe this exactly, they're equations that involve calculus. I think I will write them down carefully for you. Well, I probably can find them just on the web quite easily here. They're called Maxwell's equations, and yeah, there they are, big as life. Now they sort of went away. Where are the nice? Okay, well, these are Maxwell's equations. This one here is saying that well, here's the way I describe it to you. The average of E multiplied by surface area is equal to the charge proportional to the charge inside. And then the two ones that I described earlier, namely that if you have a magnetic field that's changing, you're going to get a circulating electric field, or if you have a circulating electric field that's changing, you get a circulating magnetic field. And here, remember over here I said if you have a current, you have a magnetic field going around it. There's the current, there's the circulating magnetic field. Del cross something, this thing is pronounced del, and the integral form is easier. You see, this says that the magnetic field going around the current here is equal to the magnetic constant, mu0 times the current, plus the surface integral of or the area of the surface times the magnitude, the rate of change of the electric field, times mu0 times the product of the magnetic constant times the electric constant. These two things are 1 over the square of the speed of light. So you see the speed of light is built into this equation. If you set this equal to 0, this essentially tells you, or these four equations tell you, that electromagnetic waves propagate at the speed of light. The speed of light being 1 over the square root of the electric constant times the magnetic constant. And this is about 300,000 kilometers per second. So that's moving along there at very high speed. This is an equation that I never mentioned to you, and I don't know why, it basically slipped my mind. It's an equation that says that if you have, say, a sphere, and you measure the magnetic field, B here, and you find it's going out there, and it's going out there, well, then you can be sure that somewhere else it's coming in like that, because the average value of B on the sphere, 0. And this is the statement that there aren't any magnetic monopoles. In other words, this is an electric charge. There's no analog for magnetic charge, at least that's ever been detected. And if there were, and there's been speculation that there might be in extended theories, then you would have a magnetic charge here, then you'd have a magnetic field there, and you'd have something like a 1 over r squared force. But there's been no detection of what's called a magnetic monopole. Now, in fact, there are some theories. These theories are not by any means, these are speculative theories. There are speculative theories in which magnetic charges occur. And for a while, these theories were very fashionable. They're still fashionable, but they've gotten a little bit long in the tooth by now. Anyway, these theories, they're called grandly unified theories, which unify the electric, magnetic, weak, and strong interactions all together, and the unification takes place at very, very high energies. Anyway, in these theories, in some of these theories, you can form magnetic charges. So then the question people were asking was, where are they? And people did experiments, didn't find any. And then about that time, this was back in the 70s, Alan Guth and others put forward the idea of inflation. Well, people said, in the very early universe, when it was very hot, there were magnetic charges created, but because the universe expanded so much, they were lost. And so, you know, there might be one per galaxy or something. So,
I'm about to say, like, how
good luck finding it, yeah.
So it's just lost in the sense that there's no hope finding one.
I'm sorry, say it again?
It's lost in the sense that there's no hope finding one, considering how vast.
Yeah, if they exist at all,
Okay.
yes. Yeah. Okay.
And that's Gremlin unified theories?
What?
How would you say it was a Gremlin?
Well, most people say grand unified theories, but I think that's kind of silly. I think the grand refers to the unification, so it really should be an adverb, grandly unified theory.
Oh, grand. Okay, gotcha.
And the area of physics is called grand unification.
Okay.
But there's no evidence for it.
Okay.
Just as there's no evidence for supersymmetry or superstrings, and there's some evidence for inflation, but it's not. There's real evidence for the Big Bang. That's pretty solid, but and inflation is the best explanation of the Big Bang and many things, but the homogeneity of the Big Bang and the isotropy of the universe and so forth. But it's not exactly established. It may be, it may become better established in the next 10 years or so, or something better may replace it. One just doesn't know. I was going to say something, but it slipped right out of my mind. Yeah, what I was going to say is that something about chaos. I think I mentioned it briefly when we had that funny pendulum that instead of just swinging like this, did all kinds of crazy motions. Well, it turns out that, as you know, there are 7 conserved quantities, or 8 really, at least. 3 of them are momentum. Momentum being, you have a bunch of particles, M1 with velocity 1. I'm writing things down non-relativistically for simplicity. M2, V2, so these are at low speeds. And so forth. So this is conventionally written as speed. I suppose that stands first letter of some Latin word for momentum, or maybe some German word for momentum. In any event, you take the sum, you count up all the particles, they each have mass M1, M2, M3, and so forth. They're moving at velocity V1, V2, V3, and so forth. You add up the products of M1, V1 plus M2, V2, and so forth. That's the momentum. In empty space, or if there's nothing acting on those particles, then that momentum is conserved. The energy that's conserved, it's actually not so much harder. Well, I mean, if I wanted to write this as, it'd be 1 minus V1 squared over C squared, square root of 1 minus V2 squared over C squared, square root of 1 minus V3 squared over C squared. So if we did things relativistically, these would be the momentum. For energies, you have M1 C squared over the square root of 1 minus V1 squared over C squared plus M2 C squared over square root of 1 minus V2 squared over C squared plus M3 C squared, C being the speed of light, square root of 1 minus V3 squared over C squared. So you'd sum up these quantities, and that would be the energy. So these are 4 quantities that are conserved. 3 other quantities that are conserved are angular momentum, and as you know, angular momentum, it basically is, we write it as L, and it would be R1 cross P1 plus R2 cross P2 plus R3 cross P3, and so forth, however many particles there are. So now we've got 7 quantities that are conserved. The other thing that's conserved is charge, of course. And there may be other conserved quantities that we don't yet understand. There probably is something else. It might be fermion number, but it might not be. These things are conserved. Now, if you have a physical system in which the number of degrees of freedom and the number in which there is many conserved quantities as there are degrees of freedom, then you can solve the equations exactly. And the motion is regular. It's basically things sort of do that, or they move in straight lines and so forth. This degrees of freedom, let me just explain how that would be. A single particle moving in 1 dimension, well, 1 degree of freedom. 1 particle moving in 3 dimensions, 3 degrees of freedom. 2 particles moving in 3-dimensional space, 6 degrees of freedom. So basically the 2-body problem you can solve because you've got 7 kinematical conserved quantities: energy, momentum, and angular momentum. On the other hand, as soon as you go to 3 bodies, then you have 9 degrees of freedom, and you only have 7 conserved quantities. So in general, the motion is, well, first of all, you can't solve the equation. The motion is said to be non-integrable. And moreover, in general, it can be chaotic. And chaotic means that, well, there are many aspects to chaos, and each aspect of chaos is similar to the meaning of the ordinary English word, you know, organized like a child's room, right? A mess. Anyway, there are many definitions of chaos, and one of them is that basically the motion, if you use computers to calculate the motion, and what you find is after a while the two trajectories that start from slightly different initial conditions start to diverge, and that motion is said to be chaotic. And so the solar system, having more than 2 bodies, is itself chaotic. Just even the Sun-Earth-Moon system, or the Sun-Jupiter-Earth system, those are 3-body problems. Poincaré, about 100 years ago, was studying this and noticed that there was this these exceedingly complicated orbits, and that's the characteristic of chaotic motion. So let's see what else. I guess I'm sort of reviewing things. As far as elementary particles go, our present understanding is formulated as the standard model of particle physics, and it's a theory in which there are a certain set of particles called fermions. These ones, all the ones that have been discovered and that are in the standard model have spin 1/2. And these particles are such that they don't want to be in the same place. You can only put one in a given state. If you have a given quantum state, you can only put one there. Let me give you a rough idea of what a quantum state is. You see, we were talking here about position and momentum. So, if you have a small amount of volume, V, and a small volume in momentum space, so this is an object that is length cubed times momentum cubed. The number of states that it has, you divide by Planck's constant cubed. Planck's constant, you remember, is very, very small. And so basically, the amount of, this is called phase space, volume in momentum space times volume in position space. Phase space divided by Planck's constant cubed, that's the number of states that you can put there. That's the number of orbital states. If you also have the possibility of spin up or spin, if the particle is spin 1/2, then you can put 2 particles there, one spin up, one spin down. So there are fermions, and these fermions are, the common fermions are an up quark, a down quark, a neutrino, and an electron. So all the ordinary matter is made out of these. There are two other families, though. Chom's strange, a mu neutrino and a muon, and top, bottom, another neutrino and a tau. And these ones up here are a little bit like the images you get if you use a smartphone to take a picture and the contrasting light is too great. You get 3 copies.
Okay.
All right. There are 3 different ones here. There's UUU, GGD, CCC, SSS, TTT, BBB. In other words, the quarks all come in 3 kinds, and these things have been whimsically called colors for, I don't think, any good reason. And I typically call them red, green, and blue, or red, green, and blue. And so we've got basically these 3 times 6, 18 quarks, plus 6 leptons. These things are called leptons. Leptos is a Greek word meaning light. And these things are quarks, and they're also called hadrons. But hadron is a much more general term. And it's from a Greek word meaning strong or stout or thick. So in this standard model, these particles interact with each other, and the principal interaction, or one kind of, the easiest interaction to visualize is a scattering interaction where they exchange where they exchange a boson of spin 1. And these bosons could be the photon, which I guess I can write as A, or they could be a W boson, plus or minus. Now the photon, of course, is massless, and so it's very easy for 2 particles to exchange a photon. In fact, they can be far apart and still exchange a photon. The W's, though, are very, very heavy, and so they're a mass of maybe 100 proton masses. And then the Z, which is neutral, is even heavier than the W, maybe 110 proton masses. And so these interactions, when they exchange a W or a Z, these are short range. And the range is so short that the interactions hardly ever occur. And because they hardly ever occurred, and people didn't understand how they occurred at all, people called them weak interactions. But they're really short-range interactions. But, as I said, people call them weak interactions. And then there's finally the strong interactions, and if you describe how particles scatter with strong interactions, well, they exchange all these gluons, and pretty soon there are so many gluons exchanged. These gluons have mass 0, and there's so many gluons exchanged that the interaction is extremely strong, and basically the charge on each, the strong charge on each gluon is also strong, and in effect, at low energies, these quarks are confined. So in high energy collisions, the quarks get shaken out, but they quickly recombine, and all you see are nucleons or mesons, which is to say bags containing 3 quarks, like a proton or a neutron, 3 antiquarks, like an antiproton or an antineutron, or quark-antiquark pairs, like the various mesons, in particular the pi mesons, which are the most common. So as I said, the standard model of particle physics describes all this, and it's a very nice picture, a very nice theory in that it works. And the unfortunate thing about it is it's not a very pretty theory. And the reason it's not very pretty is that the W's and the Z's interact in a way that violates left-right symmetry. And that's kind of weird. It's as though the standard model was like this. And I imagine in the next 30 years or so this will be fixed. Other problems are that the theory has many infinities that show up, and a better theory would not have infinities, or would have a nicer way of dealing with them. Anyway, our H2C and H2O have separated. The H2C is on the top and the H2O is on the bottom. The separation is not complete, though. You can see this is quite yellow. That's the H2C, and this is a mixture of H2C and H2O. Then we have just the H2O down there.
And so H2C is just oil, or what kind of oil?
Huh?
What kind of material is H2C?
Well, H2C is just oil. All hydrocarbons. In fact, I had intended to talk a lot more about chemistry. So I'm going to say a little bit about chemistry now. Methane. The simplest hydrocarbon is methane, CH4. And when you burn that, you get 2 molecules of water and 1 molecule of carbon dioxide. But if you have 2 carbon atoms, then imagine that there's a hydrogen at the end of each of these, okay? Maybe I'll write it in this time. And so this, with 2 carbons, it's called ethane. And now, this is still a very small molecule, only 2 carbons there, only 1 carbon here. But now you can imagine that you have a whole chain of carbons. Now, each one has 2 hydrogens. Except for the last one, which has 3, and the first one, which has 3. But the others all have 2 hydrogens. That's why I call this CH2, or to make it similar to water, I called it H2C, which is to say that the structure is basically H2C, say 10 times or 20 times, and then 2 CH3s. And that's characteristic of all hydrocarbons. If you want it to be not simply a hydrocarbon, but say a fat or an oil, then you'd have a glycerin up here, and you'd have 2 or 3 of these hydrocarbon chains. And if these chains are straight, then the molecules tend to line up parallel to each other. And they have a higher melting point. So at room temperature, they tend to be solid. And these are called saturated fats, or is this a saturated oil, or a saturated hydrocarbon. Saturated in the sense that there are as many hydrogens as possible. The opposite case is when, say, this hydrogen is missing, and so there's a double bond here. Well, if you have one or more double bonds, then it's unsaturated. This produces a kink. And these ones tend to be, if we're eating them, they tend to be crooked, and they don't solidify at room temperature because they're so crooked. And these things are healthier, basically, to eat. These are unsaturated fats. Again, the fat is when you take 2 or 3 hydrocarbons, attach it to a glycerin on top, and then it's a saturated fat. I think I'll say some more about chemistry on the last lecture, and maybe a bit about biology. Have you guys all had courses in chemistry? How many have had chemistry? Okay, sort of 1/3 or something. But when you had chemistry, did they do organic chemistry?
A little bit.
A little, yeah. That's the problem. Most chemistry courses skip the organic or do very little. And it's the organic chemistry, of course, that's relevant to biology and medicine. I mean, the inorganic chemistry you want, but I don't know, by comparison, it's not all that interesting. Okay, well, there's a sort of a minute left. Just let me mention another large class of molecules is what are called carbohydrates. Carbohydrates are just mixtures, CH2O, things like that joined together, carbon plus water. And in fact, the formula essentially is N units of CH2O. They can be linear or they can form rings, and in fact there's a great deal of variety in the structures of sugars. And the simplest sugar has 3 carbons, and then you can have one with 4, 5 carbons. One of the 5 carbon sugars is ribose, and that's one of the constituents of RNA, ribonucleic acid. And the DNA is deoxyribonucleic acid. I think I'll try to say some things about. How many have had biology?
Not college biology.
Some. But how about molecular biology? All right, I'm going to do then some organic chemistry and molecular biology on Thursday.
Sounds good to me.
All right, I think we can end this then.